Let's think about the existence of the derivative or the continuity of the derivative function. So remember, let's go back to the definition of the derivative. A function f of x has a derivative f prime of x, which is defined as the limit of secant lines, or sorry, the limit of the slopes of secant lines. Right? It is the slope of the tangent line. All right, so this derivative is not going to be continuous, or it's not going to exist when a couple different things happen. First off, maybe your function doesn't even exist. Right? If your function doesn't exist, then there's no way that you can set this equation up. Secondly, maybe this limit does not exist, right? And we've seen how limits cannot exist. If you approach something from the left-hand side and from the right-hand side and get two different values, then the limit is not going to exist. Or maybe it returns a infinity, something that's not a real number. All right, so let's see three different cases where a derivative is not going to exist. Here we have a piecewise defined function. Let's zoom in. Let's read from left to right. So if I think about all of these different x values, then every single one of them on this curve has a nice, smooth tangent line. It's well defined. It's horizontal because the function is horizontal. But if I think about the x value of -6, then there I cannot construct a tangent line. Because if I did, remember, tangent lines are the slopes of secant lines. So if I tried to construct secant lines and approach this point from the right, I get horizontal, or I get a horizontal tangent line. If I approach from the left, I'm getting something that approaches a vertical tangent line. So my tangent lines on the left-hand side are different than my tangent lines on the right-hand side. I cannot construct a well-defined tangent line at this point when x is equal to -6. The derivative does not exist here. So a jump discontinuity means the original function is discontinuous. The derivative is definitely discontinuous. All right, and as we keep moving to the right, all of these points have nice, well-defined tangent lines. So we're differentiable here. But when we get to x is equal to -2, our function doesn't even exist there, right? This function seems to have a vertical asymptote at -2. So if f of -2 does not exist, then the derivative definitely does not exist. All right, and if we jump over that vertical asymptote, we go back to having well-defined tangent lines. So our derivative exists for all of these points, except for at that cusp. If we thought about drawing tangent lines here, from the left-hand side, we have horizontal tangent lines. From the right-hand side, we have a negatively sloped tangent line. So the derivative, or the tangent line on that cusp, is not well defined. It does not exist. So if you ever have a sharp turn like this, the derivative does not exist. So I want to draw our attention to the differences between these three different points. Here at -6, although the function does exist, the derivative does not, because we have a jump discontinuity. The tangent lines are not well defined. Over here at -2, the function does not exist, so the derivative does not exist. We cannot draw a tangent line when x is equal to -2. And over here, the function exists, and it's even a continuous function, right? We can draw this without picking up our pencil. But differentiability is a stronger condition than continuity. Even though this function is continuous, you cannot draw a tangent line on that sharp turn.